record go on. Okay. Okay, last time, let's see, we end up at the type on the type of the dynamometer. Okay, on the time we did talk about the fluid already, the fluid dynamometer already. Okay, so this is the last lecture for this course. Okay, and let's continue on the type of the dynamometer that we have left last time. Okay, last time we did talk about the fluid dynamometer in which the rotor is coupled with the stator by fluid. Right. So the principle of the dynamometer is the rotor is coupled with the stator either by electrically, hydraulically, or frictions. Okay. So the first one is about the fluid type dynamometer. So the rotor of the dynamometer is coupled with the stator by the fluid. Okay. The second type is called the eddy current dynamometers. The eddy current dynamometer. This dynamometer also consists of a stator and a rotor. The stator is in the blue color and it is fitted with the number of electromagnets. The electromagnet is shown in the red color. Okay. The rotor is connected with the engine shaft here. Right? And it will rotate when the engine is running. So when the rotor rotates, right, the eddy current that happen in the stator, right, the eddy currents, right, will happen in the stator because of the magnetic flux. Okay. This magnetic flux is set up by the field current in the electromagnets and try to move the stator casing. The stator casing here will try to move with the rotor. Right? But since this casing is fixed, right, so the brake will happen. Right? The brake will happen. Right? So we can measure the torque that try to stop this stator to move. Okay. The eddy current that happen, right, will be dissipated. Right? That means when it happens, it's gone. Okay, so the heat will happen because of this dissipation. So this type of dynamometer need cooling arrangement. Right? So you will see there will be the cooling water flow in and out of these dynamometers. This picture show you the cooling part inside the dynamometer as a cooling. You can see it in the less color here. The water will go in and then will go around this red color here, which can be either the tube or the conduit, right, to do the cooling inside these dynamometers. Now, to perform the test, this dynamometer test, the loading to the engine. Okay, let me check. Okay. To perform the test, the loading to the internal combustion engine is controlled by regulating the current in the electromagnets. This current is adjusted through this direct current supply here. Okay, right. So the loading in here, right, is regulated by the current that we supply to these dynamometers. Okay, so the brake happen. Okay, the main advantage of the eddy current dynamometer are what? The first one, it will provide the high brake power per unit of dynamometer. So that means this is a very compact dynamometers one. Okay. The second one is the dynamometer offer the highest ratio up to 5:1, right, between the highest speed to the best speed at the same rated power output under the constant power speed length. What does it mean? It means that this dynamometer is suitable for a high-speed engine. The third one is the levels of the field excitations, right? The field excitations or the electric power that needed to generate the magnetic fields, which is below 1% of the total power that is handled by the dynamometer. Right? So these dynamometers are easy to control and operate because only less than 1% of the total powers that you need to generate the magnetic fields. Okay. The development, I think the number 4, yes, number 4, the eddy current that generated is very smooth, and that means the torque developed is also smooth and it is continuous under all test conditions. Okay. So the torque that you receive, right, is not fluctuated because the eddy current is smooth, right? And the eddy current is the loading to the engine. Okay. Number 5, this dynamometer can provide a relatively high torque under low speed conditions. So that means this dynamometer is good for the high torque engine, right? Not only for the high speed engine, it's also good for the high torque engine. Okay. Number 6, there is no complicated rotating part except for the shaft bearing, right? That means this dynamometer is very easy to maintain, right? To do very easy to perform the maintenance on this dynamometer because no complicated rotating part. Number 7, right, there is no natural limit to the size of this dynamometer. Right? So the machines can be either small or large to perform the test. So it's up to the designers. Right? You want to design this engine to be small or to be large, right? Because there is no natural limit to this size of this dynamometer. Right? That means no natural limits. Right? Can be small or large, right? To test the engine, or the engine can be large or small. Right? There is no like other dynamometer that there might be a limited length on testing the sizing of the engine, but this one there is no limit on that sizings, right, to test on the engine. Uh, that is the eddy current dynamometers. Okay. The third one is the more common one, common dynamometer that used in the laboratory. Okay, we call it the electric dynamometer. This dynamometer can operate either as a motor in order to start and drive the engine at the various speed, or we can operate this dynamometer as a generator in order to absorb the power output for the engine. Okay. So if this dynamometer operates as a generator, right, then the loading to the engines can be easily changed by changing the amount of the resistance in the circuit that is connected at the generator output. Right? So when this dynamometer is a generator, right, the loading can be done by changing the resistance in the circuit that is connected to the generator output. This picture shows you the test configurations of these dynamometers. Right? The left-hand side can be either a motor or the engine under test. Okay, in this picture, it looks like a motor. Okay, if this dynamometer acting like a generator, then this left-hand side is a motor, because this motor will drive the dynamometer to generate the current and the voltage. Right? Then we can use this current and the voltage to calculate the power output of the motor. Right? So not only testing for the engine, right? It can also test the motor, right? To find out what is the power output of the motors. Now, if this left-hand side is the engine, right? Then we run the engine, and the engine will drive the dynamometer. Right? Then we measure the torque. Now, not the current or the voltage that come out from the dynamometer, because it is the dynamometer, not the generator. Okay, so when the engine is here driving the dynamometer, right, we will measure the torque that happen. Right? So the torque and the speed that we measure, right, will be used to calculate the power output of the engine under test. Okay, so that is all three types of dynamometer. Right? First one is the fluid. The second one is the eddy current or electric dynamometer, electric coupled, okay, dynamometer. And the last one is also electric dynamometers. Okay, right. The last one is different from the first one in the sense that the last one, the dynamometer on the last one, can operate as a generator or a dynamometers, right? Okay. So that's why it's most commonly used in most engine laboratory. Okay. The next measurement is the measurements of the engine indicated power. The next measurements, right? The engine indicated powers. There are two methods to measure the indicated power of the engine. The first one is by plotting the indicator diagram by using a device called an indicator. The second one is by measuring the brake horsepowers and the friction powers, right? And then we can combine these two powers together in order to get the indicated powers. Okay. So let's look at the first method, right, that we are going to use, the indicator diagram. Right. In order to plot an indicator diagram, we need a device called indicator. This device will be used to measure the variation of the pressures in the cylinder over the cycles against the piston movement. Right. The piston movement that shown in the indicator diagram can be expressed in terms of volume or in terms of the crank angles. Right. So in the indicator diagram, we will have pressure versus the volume of the cylinder, or the pressure versus the crank angles. Okay. The plot of these pressure variations, right, we call it an indicator diagram here. Okay. There are two types of the indicator diagram that I already mentioned. Right. The first one, we can make a plot between the pressure and the volume. We call it a PV plot. Right. The second one, we can make a plot between the pressure and the crank angles, right? Or the P theta plots. Okay, so now on, we call it the indicator diagram. We used to call it a PV diagram, P theta diagram, but these two, right, commonly called indicator diagram. Okay, this is the example of the indicator diagram, right? The picture on this left-hand side, I think most of you should be familiar with these two pictures now. Okay, this is for the two-stroke engine, okay, and this is for the four-stroke engines. Okay, so these two pictures are called the indicator diagram. Okay, this picture show you an indicator device. The whole portion here is called the indicator device that attached to the engine under test. Right? The main components of the device are the drum here. This drum have a paper wrapping around. Right? The white color here is the paper that wrap around the drum. Right? And here is the stylus or the pen, right, to draw the diagram on this white paper. Okay, the device have the indicator cord here, right? This indicator cord here will provide the rotation motion to the drum, right, according to the piston movement, right, or the movement of the piston inside the cylinder. I do not show here, but this one, this indicator cord here will give you the piston movement to the drum here, right? Why this indicator cord can provide the piston movement to the drum? Because this indicator cord will go and connect to the connecting rod, right? That's the reason why it can transfer the piston motion to the drum here. Okay, so the drum will rotate left and right. Right, the drum will rotate left and right according to the motions or the movement of the piston. And this stylus here, the stylus here, right, will move up and down, right? Will move up and down according to what? The pressures, the pressure inside the cylinders, right? Which is the pressure force here, right? Acting against the force from this calibrated spring, right? So the difference of these two forces will determine the movement of this stylus. Okay, so the stylus move up and down, and the drum here move left and right, rotate left and right. Okay, and both two, when work together, will create the indicator diagram here. Okay, so this is another picture that show the indicator installed on the engine. This is the indicator, and this is the indicator cord that go to the connecting rod inside the engine. Okay, this is the actual indicator diagram. This is the actual one, right, that we receive from the indicator, the actual one, right? And if it plot between the pressure and the volume, right, the area inside here will represent the indicated work, right? The indicated work, not the brake work on the PV diagram here. It gives you the indicated work. So we have to measure this area inside, right, in order to determine the indicated work, right? So we need to use this device, which is called a planimeter. Right? We use this device to measure the area inside this indicator diagram here, right? By moving this device along the line in the diagram until finish, right? Then we can know the area inside this indicator diagram. Okay, so that is the first way to determine or to measure the indicated work or indicated power by using an indicator diagram. The second method, right, in order that we can have an indicator diagram, right, is by using transducers. or electronic indicator. Right? The first method we use an indicator, purely mechanics. Right? The second method, now we are going to use the electronic indicator, right? By using a transducer. So what is a transducer? A transducer is a device that can convert a non-electrical quantity or physical quantity, right, into an electrical signal. Right? Example of such a physical quantity, right, that are in our interest and can be converted into the electrical signal are what? The displacement of the piston, the velocity of the piston, right, which determine the velocity of the engine, the accelerations, and the force, right, that happen in the cylinders. These are all the physical quantity that we can convert by using the transducer into an electrical signal. Right? This can be done because of what? Because the electrical properties of many materials, right, they are changed when they are subjected to a mechanical deformation. So if this material is deformed, right, the electrical properties of this material will change, right, and we will use these change, right, in order to determine the amount of the electrical signals. So according to how much the deformation that happens, right, we will equivalent that deformation to the amount of the electrical signal here. And this is the principle how the transducer works, right? How the transducer can transform the physical quantity into the electrical quantity. Okay. This picture shows you a schematic diagram of the balance diaphragm type indicator, or sometimes they call it the balance pressure diaphragm type indicators. Okay. This is the cylinders, and this is our device. This is our device, the electronic indicators. Okay. So inside the cylinders, we have the engine pressure. Right? So the engine pressure inside the cylinders will bend this balance pressure diaphragm, or is a diaphragm. This is a diaphragm here, right? So the pressure inside here, right, will try to bend this diaphragm, right? So the diaphragm here will bend and then make contact with the pressure pickup device or the transducer here, right? So this transducer will convert the pressure force here into the electrical signals, right? And it will send this electrical signal via the induction coil here, right? In order to activate this electrode pointer. So the electrode pointer will start to do the work, or to do the writing, or to do the drawing here, right? Okay. This balance diaphragm, pressure diaphragm here, after receive the force here, right, and make contact with the transducer, right, then we will try to bend it back in order to know the pressure force, right. The pressure force here only activate the electrode pointer here, right. So this transducer, right, the job of this transducer is to receive the force and then convert into electric signal and then activate this electrode pointer, right. How about the amount of the pressure here, right? The amount of the pressure here we can determine by supplying the external pressure to this diaphragm, right? So this diaphragm will not bend, right? If this diaphragm is not bent, then we know that the amount of the pressure inside this cylinder will be equal to the amount of the external pressure that we supply from the external pressure source, right? We can adjust the amount of the external pressure source here by using this pressure control valve here, right? So when after we adjust such that this diaphragm is not bent, that means there is no electrical signal from here, right? Okay. So we know that now this pressure that we supply here will be equal to the engine pressure here, right? And the same amount of the pressure, right, will be go to this piston, right? And then force this piston to move, right? Force this piston to move so that this electrode pointer will move, right? So this electrode pointer now will move left and right according to the pressure that acting on this piston. Oh, in fact, it is not, right? According to the pressure, the difference of the pressure that acting on this piston and the pressures from the spring, right? The difference between these two, right, will move this electrode pointer left and right to draw the indicator diagram. Okay, the drum is right here with the paper, right? The drum will rotate, right? Its rotation is happen because this drum will driven by the engine shaft through the reduction gear, right? So the indicator diagram will be plotted here on this paper. Okay. Okay, the external pressure source that used here, right, is not only to do the balance of the pressures at the diaphragms, but is also to provide the work for other moving component is not shown in these pictures, right? Except for this diaphragm, because this diaphragm just bent, right? But there are other component moving. This external pressure source will provide the the work to that moving components, right? The reason is because they want to minimize the inertia of the indicators, right? Try to minimize the inertia of the indicator, which can affect the result that come out from the indicators, right? Especially when we test the engine that have a high speed, because if the engine run at high speed, or this device will move fast, right? And that means the initial effects might happen, right? And the accuracy of the diagram, right, may not be that good enough. Okay. The most, since this device depend on the pressure pickup device or the transducer. Okay, let's look at what are the types of the transducers that use. The most common type of the pressure pickup device or the transducer for the engine work are the resistive type or the strain gauge type transducers, or the capacitive type transducer, which sometimes they call it a piezoelectric element. Okay, the piezoelectric transducers. Okay. This picture show you a continuous pressure system with a pressure pickup signal or the transducer here. This is the pressure transducers or the pressure pickup device here. The pressure electrical signal, right, after it received from this diaphragm, the force, the pressure force from this diaphragm is convert this pressure force into the electrical signal. So the electrical signal is then amplified through an amplifier at C here, right, in here. And it will send this signal to the oscilloscope. Right? So we have one signal, which is the pressure signal, from the transducers. Where is another signal? Another signal is the crank angle electrical signal, theta. Right? This crank angle electrical signal is also sent to the oscilloscope here. Right? And it is received from the timing gear here that run with the engine shaft. Right? So the signal received from by using the magnetic pickup here, right? So every time that the timing gear rotate, right, the magnetic pickup here will detect the rotation, right, and send the theta signal, which is the crank angle signal, to the oscilloscope here, right? So we can see the plotting on the display on this device or the oscilloscope, right? The display. So we will see the P theta diagram show on the display here. Okay. Now, for measuring the dynamic pressures, we can also use this piezoelectric pressure sensor on the transducers. Right? The sensing element that used inside most of the piezoelectric sensor is called the quartz crystal, a quartz crystal here. Because this quartz crystal can ensure the stable and repeatable operations of the transducers here. Right? The quartz crystal here can generate the electric potentials due to the mechanical stress or the motion that happen, right? So that means we still need a motion, right? So we have a diaphragm here also in this piezoelectric transducers, right? So that this quartz can generate the electric potential here, right? So you can see here we have several quartz plates at the bottom of the piezoelectric pressure sensor that is next to the diaphragm here. Okay. Another type of the pressure transducer we call is a strain gauge transducer, or it is a resistance type transducers, right? Where we have a wide strain gauge here, right? The grid that show right in this picture is the wide strain gauge here, right? This wide strain gauge is outside of the strain generated tubes, right? It's attached to the outside of the strain generating tubes. Yeah. Okay. So when the pressures, the engine pressure acting on the catenary diaphragm, right? I think most of you remember the word catenary, right? When you learn in static, we have a catenary cables, right? Now, that is one dimension, but diaphragm is two dimensions. We can also have a catenary diaphragm here. Right? So when the engine pressure acting on the catenary diaphragm, this diaphragm will bend and convey the force to the strain gauge, right? And make the gauge to deform. Right? So the gauge resistance changes. Right? So, and by sending a small electric current to the gate here, right? Then we can determine the electrical resistance change due to the gate deformations, right? Because of the pressure here, right? But anyway, this type of transducers, right, still require cooling. Okay, so you see, we have to send the coolant into this transducer to do the cooling, right? And mostly it will use the air as a coolant. Yeah. Another type of transducer we call is the electromagnetic pressure transducers. Right? Inside these transducers, we have the permanent magnet, and we have a wiring coil, right, that make form ions. Right? It can be, for example, here 4,500 turn of the number 41 Y here. Right? So we have a wiring coil here, and we also have a diaphragm here. Right? We have a diaphragm here. Okay, so when the engine run, the engine pressure act on the diaphragm deform, right? And the deformation of the diaphragm will result in the change of the magnetic field inside the transducer, right? This magnetic field inside change because of the change in the inductance of this permanent magnet, right? So we have an electrical signal sent out, right, to determine the pressures that happen inside the cylinders. Okay, number 6 measurements is the pressure diagram, right? To plot the pressure diagram for the internal combustion engines, right? We used to talk it already in the indicator diagram, right? It's the pressure versus the crank angles. This is the theoretical one. Right? It's theoretical because what? You can see that the maximum pressures, right? The maximum pressure and the combustions happen at the top dead center. This is something that we would like it to have, right? The combustion start and finish, right? While the piston is still at the top dead center, right? So the combustion have to be very fast, right? And if it can be fast, the maximum pressure will occur at the top dead center. Okay, but in the reality, right, this is the actual pressure diagram. Right? Most of you now should be familiar with this diagram here, right? That we can see that the maximum pressure, right, is always happen after the top dead centers, right? And you can see that the pressure changes with the crank angle, right? The pressure always change with the crank angle, and combustion needs time. The spark happen here, combustion start here, and it needs time, right? In order to create the maximum pressures. Number 7 measurements is the measurement of the friction powers. Friction power. Right? Frictions always play an important role on the performance of the engines, right? Because it is the loss of the energies that we provide into the engines. Right? These friction loss, right, are dissipated to the cooling system in the form of heat. If you remember, right, when we talk about the heat transfer, the frictions and lubrications, right? Heat, the friction that happen, right, can be converted into the form of heat, right? Okay, and at a given engine speed, right, the friction power is nearly constant. Okay, so this is the good part, because if we run the engine at the constant speed, the friction power is also constant, right? So we can measure the friction powers, right? If at constant speed, the friction power is very, then it's going to be very difficult to determine what is the correct amount of the frictions, right, power at that speed. Right? So it's the good part here, so that we can do the measurements of the friction powers, right? The measurement of the friction power is important also, right? Because if we would like to know how we can improve the performance of the engine, we need to know how much is the friction powers, how much is the friction power, right? So that we can try to reduce this amount of the friction power here. Okay. So let's look at the method for measuring the friction powers. Okay. The first method is to directly measure the indicated power, right? We can measure the indicated powers from the indicator diagrams, right? And we measure the brake powers, right? From what? From the dynamometers, right? So we will measure the indicated powers and the brake powers of the engine at the identical working condition. That means we measure it at the same time, right? So the friction powers can be found from the difference between these two. Right? So we measure the indicated power through the indicator diagram. We measure the brake power through the dynamometer, and we measure these two power at the same working conditions. Okay. So this is the first method. Okay. The second method, right? We can do it by performing the motoring test. Right? I think most of you should be familiar with this word, the motoring test. Right? So in the motoring test, the engine is first run to measure the brake power at the given speed. Right? So that means we run the engine normally. Right? The engine connects to the dynamometer, and then we measure the brake powers. Right? And then we turn off or cut off the fuel supply, or we cut off the spark. Right? So the engine is down. The engine is down. And then immediately we will use the dynamometer that already attached to that engine as a motor, right? To drive the engine, right? To drive the engine back to the same speed, right? Back to the same speed before we cut off the fuel supply, and then keeping other parameter the same, right? Try to keep other parameter the same, right? And if we do this, this is what we call the motoring curve, right? So we cut off the fuel supply, we convert the dynamometer to be a motor, right? And use it to run the engines, right? Back to the same speed, right? And since we use this dynamometer as the motor, right? Okay, so the dynamometer, the motor needs the power supply, right? So we will measure the power supply to the dynamometers. Right? We measure the current, we measure the voltage that used by this motor, right? And then we can calculate the power, the electrical power that supplied to this dynamometer. And this power will represent the friction powers, right? So in the motoring test, we run the engines, right? We run the engines, and then we shut off all the power supply or the spark, right? So the engine will stop. Right? Then immediately we use the dynamometer as a motor to run the engine back to the same speed, and then we measure the power supply to that motor or that dynamometer, right? And the power supply will represent the amount of the friction powers. Okay. Anyway, even though this we can measure the friction power, but this test has a problem. So what is the problem on using this modeling test? Okay. First is the engine is not firing. Right? The engine does not operate exactly the same condition as it used to be when we run the engine by the dynamometer. Right? So that means the running conditions are not the same. The second problem is what is about the pressure and temperatures of whatever inside the cylinders, as well as the surfaces of the cylinder and the piston. Right? This pressure and temperature Now they are not the same because there is no firing or combustion inside the cylinders. Okay, so that the two problems that happen on the motoring curve, right? So the friction power here, right, is not accurate, right? But it's workable. The amount is workable, right? But in terms of accuracy, of course, because of these two problems, right, it will not be accurate, right? So in terms of engineering, it depends on the data, the quality of the data. You want the data, the quality of the data to be workable. That means you can use it. You don't need the accuracy of that data, right? It's workable for you, right? Or you need the data to be very accurate. Right? So it depends on the useness of the data here. The third test is the Morse test. The Morse test. Okay. This test is only applicable on the multi-cylinder engine only, right? So for one single cylinder engine, you cannot use this test, the Morse test here, right? It have to be used on more than one cylinder engines. Under this test, the engine is run at the required speed, right? And then we measure the torque that happens. Okay. So again, the engine have to connect to the dynamometers, right? And then we run the engine at the speed that we want to test. And then we measure the torque that happen. And then we will cut out one cylinder, right? So one cylinder will stop working. Right? So the engine speed will fall, right? Or will go down because of the loss of power by that cut out engine, cut out cylinders. Right? So when we cut out one cylinder, the engine speed go down because we lost the power from that cut out cylinders. Right? And then after that, in order to regain the same engine speed, we will reduce the load. We will reduce the load to that engine. Right? So when we reduce the load, the engine go back to the same speed. Then we measure the torque again. We measure the torque again, right? When the speed go up to its original one. Okay, before we cut out one cylinder, right? Just cut out only one cylinder. Okay. Okay. So now, if we denote the indicated power of each cylinder by what? By I1, I2, I3, and I4, right? All of these are the indicated power from each cylinders, right? If we considering on the 4-cylinder engines, right? Okay. The power loss in each cylinder, right? We can also denote it by L1, L2, L3, and L4, right? So by using this symbol for the indicated power and the loss, this symbol for the loss, right, which represent in each cylinders, right? So for normal operation, that means we run the engine in the normal conditions, the brake powers from this engine can be determined from what? The indicator powers minus the loss power or the friction powers, right? For each cylinders, right? Sum all of this together for each cylinder, then we will get the brake powers of the whole engine under normal operations. And now, if number one or the first cylinder is cut out, right, that means what? The contributions of the indicated powers, right, from the cylinder that is cut out is gone. It's gone, no more, right? And if the losses due to that cylinder, which is L1, remain the same because the piston inside the cylinder still moving up and down, right? As when it is firing, after the engine reaches the same speed, then what we have will be what? Right? When the first cylinder cut out, we don't have the indicated power from that cylinder, but we still have the loss that happened inside that cylinder because the piston inside that cylinder still go up and down. Right? Then what we will have for our new brake powers, BP1 will be what? Will be according to these expressions, right? We still get the same brake power from all the rest of the cylinder that is still working, right? The first cylinder, we have the negative powers, which is the loss, right? So if we bring, right, if we combine the two brake power together, right, that means the brake power before we cut down one cylinder, right, and the brake powers after we cut down one cylinder, right? We minus the brake power before with the brake power after. What we receive is what? The indicated powers from the first cylinders, right? So if we do it again and again, by doing the same by cutting out each cylinder in turn one by one, right? So the value of I2, I3, and I4, which is the indicated power from the second, third, and fourth cylinder, right, can be obtained. And that means what? We can determine the total indicated powers, right? And then the friction power can determine from the difference between the indicated powers and the brake powers. Okay, so this is what we call the Morse test. Cut out cylinder one by one, right? By first measuring the normal operation of the engines, right? Measure the brake powers, and then we cut down one cylinder one by one in order to determine the indicated power from each cylinder. Right? And then sum all indicated power altogether to get the total indicated powers. Right? And then using the indicated powers and the brake powers, right, in order to determine the friction power here. Okay. The fourth method, right, to measure the friction power is to use the wheel length line. The wheel length line, right? In this method, we have to create a graph, and that graph is called the wheel length line. The graph is done by making a plot between the measured gross fuel consumptions and the measured brake powers at a constant speed, under several loading conditions, right? So that means we will have different brake power, different gross fuel consumptions at a constant speed here, right? So when we make a plot, it's going to show on this dark color here, full line, dark color here. Okay, that is a plot between the gross fuel consumptions and the brake powers at a constant speed here. Now, after we getting this Wheeler line, here, then we will further extend this line, right? We further extend this line to the point where the fuel consumption becomes zero, right? This point is the fuel consumption is zero, in which this will give you a negative brake powers. a negative brake power, right? We consider this is the power loss, right? This negative power or the power loss is also equivalent to the point, right, where we have the brake power equal to zero, or in other words, it equivalent to the power, right, when our engines consume this much fuel consumption at this point B, right? Because point B show you that we have the amount of the fuel consumption to the engine, but the engine provide no brake powers, right? So A give you the negative power, brake power, which is considered to be the power loss. B give you the amount of the fuel consumption when this engine deliver no work, right? No brake power. So they both are equivalent with each other in the sense that these two represent something that we do not get, but we have to pay for, right? We do not get the brake power out, but we still have to pay for the fuel consumptions, right? And we do not get the power, the brake power here, right? It turned out to be the power loss, right? Okay. So this is how we can determine the power loss or the friction loss by further extend this Villen line, right? And we can determine the amount of the fuel consumption that is equivalent to this power loss here. Okay. Unfortunately, that this Villen line test, right, or method is only applicable to the compressed ignition engine only, right? You cannot use this test on the spark ignition engine. The reason is because in the spark ignition engines, right, we do have the pumping loss. We do have the pumping loss here that occur during the low speed. And this pumping loss is due to a very low amount of the air fuel mixtures, right? So there is a low pressure regions that is created inside the cylinders, in which the engine have to keep out its work, right? So it is the pumping loss here, right? Show in here, the pumping loss here, right? And that means what? That means this loss, this pumping loss is not a friction loss, right? So if we take the Whelan line method on the SI engines, right, the negative brake power that we determine, it will not only be the friction loss, right? It is also include the pumping loss as well, right? So the friction, the power loss here is not only the friction loss, right? It includes also the pumping loss here, because pumping loss is the negative work or negative powers, right? Okay, the engine have to pay for in order for the engine to draw the air and push the exhaust out from the engines. Okay, so that's the reason why the spark ignition engine cannot use the Whelan line method here. Okay. Okay, the next one is heat balance of the engines. Okay, the last one. This is the last one. We used to talk about the heat balance already in the performance of the engines, if you remember in our previous lectures. But in the testing of the engine, heat balance is still important to mention. Okay, to mention again here, like in the test. Right? So not only the performance of the engine that we need to concern about the heat balance, on the testing of the engine, we also need to concern about the heat balance. Okay, so the main component of the heat balance are what? The heat equivalent to the brake powers of the engine, okay? The heat that is rejected to the cooling media, and the heat that is carried away from the engine with the exhaust gases. And the last one is the unaccounted heat losses, right? Or sometimes we call it losses here. Okay, this diagram show you the approximate number of each heat that we just mentioned. Right? About 30 to 40% of heat go to the brake powers, 20 to 30% go to the cooling water, 30 to 35%, right, go to the exhaust gases, and 5 to 50%, right, go to the unaccounted losses. Okay, this is also another table show you the approximate percentage of the various loss that happen in the SI and the CI engine, right? So this is the actual value come out from the test. They give you the length of the number of losses that go from each heat here, okay, for the SI and the CI engine, okay? So you can take a look by yourselves. Okay. Okay, so that is for the testing of the engines, right? That is normally done in the engine laboratory, right? Take measurement all together. Okay, let's look at the examples. At the example, if there is no question, any questions for the testing of the engine, start from dynamometer, indicated power, pressure diagrams, right? Friction powers, okay, and the heat balance. Okay. Is there any questions? If not, then we will go for the examples. Okay. The airflow to a four-cylinder four-stroke engine is 2.15 cubic meter per minute. During a test on the engines, the following data were recorded. The bore is 10 to 5 centimeter. The stroke is 12 to 5 centimeter. The engine speed is 1200 RPM and the torque is 150 Newton meter. The fuel consumption is 5.5 kilogram per ounce and the calorific value of the fuel is 43,000 something kilojoule per kilogram. Right? The ambient temperature and the pressure are 20 degrees Celsius and 1.03 bar. Okay, the atmospheric conditions. Calculate from all this information that you get from the test, the engine test, the brake thermal efficiency, the brake mean effective pressure, and the volumetric efficiency. Okay. So we know the torque, right? We see from the test, we know the engine speed, right? From speed measurement, then we can calculate the brake powers, right? And when we when we know the brake power, then we can go further to calculate the brake thermal efficiency, right? The brake thermal efficiency, according to the definition, we already know the amount of the fuel consumptions when we know the heating value, right? So after we know the brake power, we can calculate the brake thermal efficiency, right? Now, how about the brake mean effective pressures? Right? By definitions, we already know the brake powers. Right? We have to calculate the displacement volume of the engines, right? And we know the speed of the engine. Okay. The displacement volume of the engine we already know the bore, we know the stroke, and it is four cylinder altogether. So don't forget to time it with four because we're talking about the total engine displacement volume, right? So there are four cylinder altogether. So we need to time it with four here, Right? Then we can calculate the brake mean effective pressures. Okay. The next one is calculate the volumetric efficiencies. Right? We know the amount of the actual air volume flow rate to the engine which is given. Right? We know the engine displacement volume. Right? So we have to change this engine displacement volume into the rate of the volume. Right? The rate of the volume, right, of the engine displacement. Right? So we can do this by timing the displacement volume with the speed of the engine. Right? So every time that we talk about the rate of the engine, don't forget the engine speed here. Right? The engine speed here. So we time the engine displacement volume with the engine speed. Right? So we get the rate of the volume flow rate of the engine displacement. Right? So by definitions of the volumetric efficiency, right? Now we have all the information we need, and then we can calculate the volumetric efficiency, which is equal to 82.73%. Okay. So this is the first example. The second example, right, a four-cylinder petrol engine has a bore of 57 millimeter and a stroke of 90 millimeter. Right? Its latest speed is 2,800 RPM, and it is tested at this speed against a brake, which is a torque, which had a torque arm of 0.356 meter. Right? The net brake load, which is a brake here, right, is 155 newtons, and the fuel consumption is 6.74 liter per hour. The specific gravity of the petrol used is 0.735, and it had a lower calorific value of 44,000 something kilojoule per kilogram. A Morse test, right, which is the friction power test, right, to determine the friction power, is carried out, and the cylinders are cut out in the order of 1, 2, 3, 4, right? And by cutting out in order, right, you get the corresponding brake load. It's a brake load, a force, not a work, not a power. Okay, it's the force, a brake force of 111 from the first cylinder, 106.5 from the second cylinder, 104.2 from the third cylinder, and 111 Newton from the last cylinders. Okay, so calculate for this speed after you perform the Morse test. The engine torque, the brake specs, the brake mean effective pressure, the brake thermal efficiency, the brake specific fuel consumptions, the mechanical efficiency, and the indicated mean effective pressures. Right? So you perform the Morse test, and then they ask you to calculate all the performance parameters of this engine. Okay. So first start with the torque, because we know the brake load, right, which is 155. We know the torque arm, right? So we know the torque. And since we know the torque, right, we know the speed of the engine, we can determine the brake powers. Right? And since we know the brake powers, right, we know the displacement of the engines, right? We know the speed of the engines. Then we can determine the brake mean effective pressures. Right? We can determine the brake mean effective pressure. Okay. The amount of the fuel consumption they give us is not in the term of the mass flow rate. Right? It's given in the term of the volume flow rate because it is a liter per hour. So we need to use the specific gravity that is given to convert from liter per hour or per second, right, into kilogram per second, right, by timing the the volume flow rate of the fuel with the specific gravity of the fuel. Okay, the specific gravity is what? Is the density, right, of the fuel compared with waters. Okay, compare with waters. Okay. 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 Then we know we know the mass flow rate of the fuel, right? So we can determine the brake thermal efficiency. Okay. And we can also determine the brake specific fuel consumptions, right? Because we know the mass flow rate of the fuel, we know the brake powers. Okay. How about the indicated one? Okay. Right. We know the indicated load from the Morse test, right? We know the indicated load we can find the indicated load, right, from the Morse test, right, from the given data, right? The indicated load for the first cylinder is what? The total brake load minus the brake load from the first cylinders, right, which is 1/11, right? So the indicated load from the first cylinders will be 44 newtons, right? B1 is the total indicated load from all cylinders except the first cylinder because we cut down the first cylinder, right? B2 is also the total brake load, right? Except the brake load from the second cylinder. B3 and B4 are accordingly, right, as we just mentioned, right, for B1 and B2, right? So, and B here is the total brake that come from 4 cylinder altogether, right? So the indicated load here from the first, the second, the third, and the fourth cylinder then can be determined, right? So the total indicated load, right, will be all of these indicated loads, sum all of this together, right? So the mechanical efficiency now can be determined from the total brake load divided by the total indicated load, right? The same thing, right? As the brake power divided by the indicated power, because they are at the same speed, at the same engine speed. That's why we can define this mechanical efficiency in terms of the brake load divided by the indicated load, right? The main reason is they are at the same speed, engine speed, right? So the mechanical efficiency become 82.8%, right? How about the indicated powers, right? When we know the mechanical efficiency, then we can determine the indicated power because we know the brake powers, right? And since we know the indicated power, we can also determine the indicated mean effective pressures. Okay. Okay, so that 2 examples, right? Okay. Is there any questions on the 2 examples? Okay. If not, then we go to the next topic. Right. Now we go out from the performance and testing of the engine. We are going to look at the engine performance characteristics. Okay, we are going to look at the engine performance characteristics. Right. There is a number of standard parameters that are available, right, for comparing the performance of the engine. Right. In order to look at the performance characteristic, right, we need to be able to compare the standard parameters of the engine under test, right? And that standard performance that we use to compare are what? The first one is the specific fuel consumption, if you remember, right? That when we want to compare different engines, right? This is the parameter that we use to compare, right? The specific fuel consumptions, the brake mean effective pressure. This is the two parameters that we use to mention. The next one is the specific weight, or the weight of the engine per kilowatt. Right? This is, we want to look at the compactness of the engine, same as the last one. The specific output, which is in terms of kilowatt per cubic meter, or the sizing of the engine, right? How compactness of the engine is, right? In order to deliver the work or the powers. Okay, so these last two we can imagine on the sizing of the engines. Okay, the first two one is truly the performance of the engine, right? In terms of kilowatt, in terms of fuel consumptions. Okay. Anyway, most of the performance factor that we just mentioned are directly related to the atmospheric conditions, right? So that means it is very, very important, right, to keep in mind that when you perform the performance comparison between the engine, or when you're doing the test in order to compare the performance of the engine, right? Those engines should be done or should be tested at the similar atmospheric conditions. Right? So if you want to compare the performance of different engines, right, you should run it at the same engine test laboratory. Right? Not one engine perform in one place, another engine perform in another locations. Right? They, it's best if these two engines can perform the test on the same condition, because all the parameter, most of the performance parameter are directly related to the atmospheric conditions. Okay. Okay, so that is the cautions. That is the caution when you want to compare the performance of different engines. Okay. Okay. Let's look at the test in order to see the characteristic on the performance of the engine. Right? The test on the internal combustion engine can be divided into three types, right, in order to look at the characteristic of the performance. The first one is the variable speed test. The second one is the constant speed test. And the last one is the consumption loop test. Okay. Okay. For the variable speed test, right, there are two tests. The first one is the full load test with the spark ignition engines. Okay. In the full load test, the throttle valve have to be fully open. Right? So the engine has to run. Right? The engine has to run at the lowest desired speed. Right? This lowest desired speed can be maintained by adjusting the loading on the engine. Right? The brake load adjustment is mean we adjust the loading that happen to the engine in order to maintain the lowest desired speed here while the throttle is fully open. Okay. The spark of the engine is also adjusted in order to give the maximum power at this speed. So in this test, on that lowest speed here, we want to see that what is the maximum power that can come out from these engines. Right? So the spark plug have to be adjusted in order to get the maximum power from the engine. Then after we get the maximum power from the engine, we will measure the fuel consumptions at several times in the world, not only once. Right? That means we keep the engine running and then we measure the fuel consumption at different times. Okay. And then after we picking up all the data that we have, that we need, right? Then since we have so many data, right? So we have to calculate the average value, right, for all parameter concerns, such as the brake mean effective pressure, the indicated mean effective pressure, and the mechanical efficiency. Okay, so this test is done under fully throttling. That means the throttle valve is fully open, the engine run at minimum speed. Right? We try to get the maximum power output come out from the engine, and then we measure the fuel consumptions, and we also measure other parameters, and then we calculate the average value of all of these parameters together. Then after finish the first run, right, that we just described before, right, which is at the lowest desired speed, right, then we perform the next run. The next run is done at several different speeds. That means start from the lowest speed, we increase the speed and perform the next test, do the same way, right? And that means in order to increase the speed, then we need to adjust the load, right? We need to adjust the load to keep the engine speed constant again, right, at the new engine speed for the next run, okay? And then we do this on and on, right? Increasing the speed, adjusting the load to keep the speed constant, right? The throttle valve still fully open all the time, right? No matter what speed it is, the throttle valve is fully open. And then we measure the fuel consumption. We try to get the maximum power out from that speed, right? So after we finish all the test run here, right, all of the correct data will be plotted, right? It show on this graph for the different engine speed here, right? This graph is a plot between the engine power, right? You can see we have indicated power, we have the brake powers, we also have the indicated mean effective pressure and the brake mean effective pressures, right? And also the mechanical efficiency for different engine speed here. Okay. So all of these are under fully open throttle, right? Fully open throttles. Okay. This graph show you the volumetric efficiency, right? Also at different engine speed. Okay. So this is what we call the full load test. Full load test. Full load means throttle is fully open or wide open. Okay, and we test it at different speed. Okay, and this is what we get from the test. Okay, the second test is the part load test. Right. So okay, so you can see the characteristic of the performance of the engine. Right. You can see how the brake power vary according to the engine speed, the indicated power, the brake mean effective pressure, and the indicated mean effective pressure. Also the mechanical efficiency, how it vary with the engine speed. This is what we call the performance characteristic. Okay. The second test is the pass load test. A part load test is the engine test at variable engine speed as well, right? But this variable speed will be at half speed, right? Half speed of what? Half speed, right? On the on the power leading of half the maximum power, right? So we will set the speed at half of the speed from the full load test, and at that half of the speed we will put the loading on the engine and adjust the spark such that the power delivered will be half of the maximum power at its speed here, right? Half of the maximum power we know from what? We know from the full load test, right? So we adjust by varying the throttle. Now our throttle is not fully open, and we also change the loading, right? Which is we call the brake setting, right? The loading on that. The second test is the constant speed test, right? So the first test, we have two tests, like variable speed test. One is the full load test, and another one is the part load test. The part load test is at half of the maximum powers, right? And we vary in order to get half of the maximum power by changing the throttle and the loadings on the engine, right? So this is the part load test. Okay. So we have full load and part load test on different engine speed. The second test is the constant speed test. The constant speed test. It is a test that runs at the constant speed now, right? With variable openings of the throttle valve from zero load to full load, right? So the positioning of the throttle valve is vary, or the position of the throttle valve vary from zero load to full load, but the engine speed is always constant, right? So the way we will vary in a suitable step of the load in order to get a smooth curve when we make a plot. Okay, so the throttle valve is first open at the zero load, right? It's open at the zero load to give the desired constant speed. Right? Then after that, a load is put on the engines. Right? So when the engine receives the load, we have to adjust the throttle valves, right, to open wider, right, to open wider in order to maintain the same constant speed as before, right? So when the engine go back to the same speed, after we adjust the throttle valve so that the engine go back to the same speed, that means we finish the first test. We finish the first step, right? And don't forget, we have to measure all the parameters, right? After the engine go back to the same speed, okay, by varying the throttle valves. Okay. We do this again and again, right? We do this again and again, right? By changing the loading, right? And let the engine go back to the same constant speed, right? The original speed one, right? And when we change the loading, we adjust the throttle valve, right, until we go to the last run of the test. The last run of the test happens when what? When we can no longer open the throttle, or cannot get the throttle valve to open wider than this. That the maximum opening or fully open of the throttle valve. This will be the last run of the test. Okay. Okay. So in the compressed ignition engine test, if you perform this constant speed test on the compressed ignition engine test, right, you will see that the last run, you will see the smoke come out in the exhaust gas, right, because it's fully open, right. In the CI engine, definitely you will see the smoke come out. Okay. This graph show, right, the test results from the constant speed test, right. Each line here represent the constant speed of the engines, right. It is the plot between the specific fuel consumptions and the brake powers. Right? And you can see the variations of the brake specific fuel consumption with the brake power at each constant engine speed here. Okay. The far right side on each line here represent the fully open of the throttle valve because it cannot go any further because since the throttle valve is fully open already. So the far right side here, I give you the sense that this is where the throttle valve is fully open. Okay. The graph show also that the brake powers, you can see that the brake power increase and the SFC decrease. Okay, so this is the characteristic of the engine performance. Okay. The last test is the consumption loop test. The last test is the consumption loop test. This is the test that carry out at 3 conditions altogether. These 3 conditions are what? First is constant speed. Second is constant throttle opening. We do nothing on the opening of the throttle valve. And the last one is the constant ignition setting. Okay. So all of these 3 have to be kept constant. Okay. And if we perform the test under these conditions, what we will get is shown right here when we make a plot between the brake specific fuel consumptions and the brake mean effective pressures. We make a plot between the brake specific fuel consumption and the brake mean effective pressure. The graph that we get, we call is a hook curve because it looks like a hook here. The right hand side of the hook curve is for the engine that run at the least mixtures, right, with the air fuel ratio equal to 10 here. Air fuel ratio equal to 10, right? The number in the graph show you the amount of the air fuel ratio. So point A is the test when the engine run at the least mixtures, right? The left hand side, which is point E here, along the left hand side here, right? The engine run at the lean mixtures. Okay, and the point C here is where we have the engine run at the stoichiometric, right? So anything on the right hand side here, right? The engine run at the least mixture. Anything on the left hand side here, the engine run at the lean mixtures here. Okay. Okay. So you can see that the air fuel ratio is at a minimum at A because this is the last point, right? So if we increase the air fuel ratio, that means we go along in these directions, right? What you will find that on the way that you increase your air fuel ratio here, the brake mean effective pressure also increase, right? Keep increasing until a maximum brake mean effective pressure is reached at point B here. Point B. This is where you will get the maximum brake mean effective pressure, right? And any further increase in the air fuel ratio, right, will produce a decrease in the brake mean effective pressures, right? But the brake specific fuel consumption still keep reducing, right? If you follow from A to B and go beyond B, right, the brake specific fuel consumption keep decreasing, right? But the brake mean effective pressure also reduce, right? Also reduce. Okay. Okay. Until what? Until the minimum brake specific fuel consumption is reached at point D here. This is the point where you will get the minimum brake specific fuel consumptions. Now, if you continue to increase the air-fuel ratio, beyond point D here, right, you will see that now you get the brake mean effective pressure decrease, which means your power, your engine power also decrease. And you also have the increase in the brake specific fuel consumption, right? That means it's not good, right? It's not good. The characteristic of your engine now is not good, right? Because you have the minimum brake specific fuel consumption at point D here. Any further increase in the air-fuel ratio result in the increase in the brake specific fuel consumption, right? And also decrease in the brake mean effective pressure, right? So both one increase and one decrease, right? In which you do not want your engine to happen. Okay. Okay. Now, for the engine that run near point A, right? That run near point A, right? The engine could be run unsteadily, and the combustion of the mixture in the exhaust system might happen because of the least mixtures. That's the reason why this is the furthest point that you can run, right? The farmost point that you can run, because your engine will not run steadily. And another thing is you might have combustion happen in the exhaust system. Okay. And at E here, which is the leanest mixture, Okay. Okay, so this is also the furthest point, the farmost point on the left-hand side, right? It's farmost because the engine will also running at the unsteady conditions, right? And the combustions may be slow, right? Since the combustion inside the cylinder happen to be slow because of it's a very, very lean mixtures, right? So the rate of combustion become low. So the engine run unsteady. So for A and B, A and E here, right? We cannot go any further from this point because our engine now is not running at the smooth conditions, right? And apart from that, at point A, since it's a least mixture, you might have combustion happen in the exhaust gas. And at point E, your combustion rate become low due to the very, very lean mixtures. Okay. And point C, of course, our engine is run at the stoichiometric ratio. Right? Now, for multi-cylinder engines, right? That is for the single cylinder engines. Right? Now, for a multi-cylinder engine, the consumption loop are not much different. Right? So they have the same trend of the hook curve. Right? And in fact, they are generally similar to that for a single cylinder engine. Right? So no matter it's a single cylinder engine or multi-cylinder engine, right? If you run on the consumption loop test, the hook curve will look similar like this. Okay. Okay. Now let's see that if we do a consumption loop test on the part throttle opening, right? We do the consumption loop test, but not at one position of the throttle opening. Right? We changing the throttle opening positions, right? What would happen? Right? It show right here. Show right here. That means we will have several hook curve because each hook curve represents one opening positions of the throttle. Now we change the throttle opening positions. That means we have more than one hook curve, right? And in this graph, right, the hook curve, if it go in these directions, right, that means we are in a decreasing throttle opening, or the throttle open less and less and less along these directions. Okay. Now, under the path throttle opening, this is what we call several path throttle opening. Right? If we put the point, right, where we have maximum brake mean effective pressure, right? This is the point where we have the maximum brake mean effective pressures, right? The blue dot here, right? This is the point where we have the maximum brake mean effective pressure for each hook curve here. And the red dot here represent the minimum specific fuel consumption for each hook curve here. Okay. After we locate all this point on the hook curve, on each hook curve, then we connect this point all together. Right? We connect this point all together. So the first line here, which is the blue line here, right? It is the line that we will get the maximum brake mean effective pressure if we keep our engine running along this line. Right? This is what we call the power mode, in the engine. Right? And if we run our engine along this left line here, right, we can be sure that our engine will consume minimum fuels all the time. Right? Along this line, we will get minimum fuel consumption. Along this line, we will get maximum brake mean effective pressures. Right? So the first line, which is the blue line here, is called the power mode. The left line here is called the econo mode. Okay, econo mode. I think some of you may see in your car, right? Some of you may see in your car that some car we have a green button, that is called the econo button. Right? If you push on this button, now you are commanding your engine to run along this red color. Right? Because all the information here will send to your engine ECU, right? The electronic control unit. Right? And when you press the green button, right, that means you are running on the econo mode. Right? The ECU will order the engine to run at these conditions. So all the parameters will be adjusted according to this less color here, right? So every time that you step on your pedal to accelerate your car, right, you can be sure that your engine now consume minimum fuel consumption. Right? In some other car, right, they may have a less button, which is the power mode. Right? So every time that you press on that left button of the power mode, right, it means every time that you step on your pedal, the engine will give you the maximum brake mean effective pressures, right, or the maximum power that that engine can deliver at that speed. Okay, so this is what we call the testing at the path throttle openings. Right? Changing the throttle opening to see how it changes on the engine performance. Okay. Okay, so that is it. I think, okay, that the end of our lecture and also the end of this course. Okay, the last lectures. Okay, any questions? Any questions? มีคำถามอะไรไหม มีไหม No เงียบเลย Okay, if there is no questions, okay, as I already mentioned earlier that our final exam will be according to the schedule on the registration office, right? It's gonna be on 12th, Wednesday, 12th May, okay, on Wednesday, 12th May. Okay, I changed the time, right? In the next, like they said, 8:30 to 11:30, right? But we're going to change the time from 9 o'clock to 12 o'clock. Okay, it's 3-hour exams. Okay, and I will send you the regulations how to arrange your exam place, which is your house. Okay, briefly, you have to set your table facing the wall. Okay, that means you are now your face facing the wall. Okay, and your size, right? On your side, you will have a notebook that you can look on the exam problem. Right? I will give you a specific time on each problem, right? And after the time is finished, then you have 5 minutes to scan your answer and send it to my course view according to the folder for that exam problem. Right? We will have 5 exam problem altogether. Right? So that means in the my course view, we will have 5 folder. Right? And you have 5 minutes after the exam finish on each problem to do the scanning and send your file into the my course view. Right? After 5 minutes finish, you can no longer send your exam paper. Right? After 5 minutes, you can no longer, because I will lock that folder. You cannot no longer send into that folder. Each exam problem will have different folder, not the same folder. Okay, so this is briefly the regulations. But anyway, I will give you more information on this exam regulation and also the picture that show you what is the correct way to arrange your exam stations in your house. Okay. Okay. Is there any problem? มีไหมถ้าไม่มีนะครับ ก็ขอปิดการบรรยายในวันนี้นะครับ เพียงเท่านี้ Okay. So see you on the exam day. Okay. Bye bye.
ขอบคุณครับ
ครับสวัสดีครับ
ดีครับ
ครับ